Hello student, today I am going to start your Thevenin's and Norton theorem. Under this we can able to solve the complex circuit and we can able to calculate the load current and load voltage with the help of Thevenin's and Norton theorem. Yeah, under this Thevenin's theorem you can see that the network 1 and network 2, two networks are there and they are coupled through A and B. Actually, the purpose of discussion at this point, we consider that both the networks are composed of resistor and independent voltage and current sources. So here, the network 1 and network 2, both having the resistor and resistor composed of resistor and independent voltage and current source. Here also in network 2 also independent voltage and current source and resistor are there. So therefore, you can able to find out the what is the amount of current flowing from the network 1 to the network 2 and what is the voltage drop between the terminal A and B. So we have to simplify this circuit. So for that, what we can do here, maybe the network 2 is actually the only resistor is there connected to network 1. So that one we can consider as a load. Okay, and here suppose the network 2 is detached from the network 1 and we focus temporarily only on the network 1. So here network 2 is detached. This is the open terminals between are A and B. Here network 1 can be the complicated in structure as one can imagine. Okay, so here we can see that the now place a voltmeter across the terminal A and B and read the voltage. We call this the open circuit voltage between the terminals A and B. So this is the actually the open circuit voltage here. So we can able to measure the voltage by using the voltmeter between the terminals A and B. So here now place a voltmeter across the terminal A and B and read the voltage. We call this the open circuit voltage. No matter how complicated network 1, we read one voltage, it is either positive at A with respect to B or negative at A with respect to B. Okay, here we call this voltage the VOS, or you can say the open circuit voltage, or we can also call it V Thevenin's voltage, because we are assuming that the between A and B the load was connected. Now it is actually act as a open circuit voltage. We have to find out the open circuit voltage between the terminal A and B. Now deactivate all sources of network 1 to deactivate a voltage source. We remove the source and replace it with the short circuit. To deactivate a current source, we remove the voltage source. So here what is actually to find out the resistance, Thevenin's resistance, we can deactivate the voltage source and current source to find out the resistance. So here let us assume this is the circuit you have. How we deactivate the sources? So we can deactivate the sources. This one is the current source. This one is the voltage source, current source, voltage source, and the resistors R1, R2, R3, R4 are connected between the terminal A and B. This is the open terminals. Okay, so here we can able to find out what is the voltage between the terminal A and B. That should be the open circuit voltage. Here Thevenin's theorem. So under this actually we have to disconnect the current source and we have to sort the voltage source. You can disconnect the current source, means you can remove the current source from the current source between the terminal of the current source, and you can sort the voltage source. This is the sorted. Previously it was the voltage source, now it is sorted. And here previously it was current source, now it is open. Then only we can deactivate the voltage and current source. Okay, so here you can see that now the ohmmeter AB and the resistance, you can connect the ohmmeter. Ohmmeter means what? You can find out the resistance here, equivalent resistance between the terminal A and B. This is the R equivalent between the terminal A and B. Whatever the equivalent resistance you can able to find out between terminal A and B, that is actually the Thevenin's resistance. Okay, so here that previously we calculated the Thevenin's voltage. Now it is Thevenin's resistance. You have to connect in series. We call the ohmmeter reading, and under this condition the Thevenin's and the Thevenin's resistance and the what we can say the Thevenin's voltage. You have to connect these two in series. Okay, so here we can now tie the network 2. So here tie network 2 means we are connecting the load again, and whatever, let us assume this is a load, so we can able to say this is the Thevenin's voltage VTH here, and this is the Thevenin's resistance we calculated already. This is the load across the network 2 RL, you can say. So now you can able to find out the current in this circuit, by applying the KVL. So here we can now make any calculation we desire within the network 2, and we will give the same result as if we still had the network 1 connection. So now Thevenin's theorem. It follows that we could also replace network 2 with the Thevenin's voltage and Thevenin's resistance. Let us assume if you have another circuit, you can also replace that one with the Thevenin's voltage and Thevenin's current resistance, and after that you can solve the circuit. Okay. Now let us assume take the example. This is your load. You have to find out the Thevenin's voltage across it, and this is the supply voltage here. Internal network 1 having the resistance 12 ohm, 6 ohm, and 4 ohm. You have to find out the voltage across the terminal A and B. So for that you have to open the terminal A and B. Open the terminal, and that one you have to remove the 2 ohm resistance from the terminal A and B. So here we removed this resistance here. Now you can see that what is the voltage across between the terminal A and B. Actually here in 4 ohm resistance there is no current. Therefore voltage drop due to the 4 ohm resistance is 0, and only the voltage drop between the A and B. Between the A and B you can calculate that voltage drop between the A and B is actually the voltage drop due to 6 ohm resistance. Okay, 6 ohm resistance. So for that you have to find out the current between current in the 6 ohm branch. So what is the 6 ohm current in the 6 ohm branch? That is equal to 30 voltage by resistance in series. So 12 plus 6, that is equal to 30 by 18. So here 6 3 ja 18, 6 5 ja 30, that is equal to 5 by 3 ampere, or you can say the 30 by 12 plus 6. Then that this current actually we have to multiply with the resistance, then you will get the voltage across the between the terminal A and B, because of this is having the 0 voltage, and this voltage drop is going to appear between the terminal A and B. That's why we are getting the voltage between the terminal A and B, that is equal to 10 volt, that is equal to current times 6 ohm, that is equal to voltage between the terminal A and B. Understood? So hence we can able to show that, notice that there is no current in the 4 ohm resistor and AB is open, thus there can be no voltage across the resistor 4 ohm, and then that's why we can say that the 6 ohm resistor voltage drop is going to appear between the terminal A and B, that is the output, or you can say the Thevenin's voltage, open circuit voltage. So Thevenin's voltage are also known as open circuit voltage. So here Thevenin's voltage or open circuit voltage is known as 10 volt. So now you have to find out the Thevenin's resistance. For that you have to deactivate the voltage source. So now we deactivated the voltage source. We are just doing the short circuit of voltage source here. So you can see that now deactivate the source to the left in A and B, and we find the resistance. Now resistance, if you see the resistance from this side, this two 12 ohm and 6 ohm are in parallel. 12 ohm and 6 ohm are in parallel, and that is in series with the 4 ohm resistance. That is in series with the 4 ohm resistance. Hence you can say the 12 when two resistors are in parallel, you can find out the equivalent resistance by R1 into R2 by R1 plus R2. R1 into R2 by R1 plus R2, that is equal to R parallel when two resistors are connected in parallel. So R1 into R2 by R1 plus R2. So we are assuming that this is the R parallel. So here let R1 is equal to 12 ohm and R2 is equal to 6 ohm. So hence we can say that this is equal to this. So here 12 6 ja 72 and 12 plus 6, that is equal to 18. So this is equal to 4 ohm. So now 4 ohm, this 4 ohm resistance is in series with the 4 ohm resistance. That's why 4 plus 4 is equal to 8 ohm. What resistance is the Thevenin's resistance? Thevenin's resistance. So we can say that this Thevenin's resistance you can connect with the Thevenin's voltage, what what we calculated earlier. This is the Thevenin's voltage we calculated earlier, that was 10 volt, and Thevenin's resistance is the 8 ohm, and here these two are connected in series. Now we can connect the load. Initially, what was the load is given to you in the question. That load you can connect here, 2 ohm resistance, and that this way you can able to find out the current in the circuit. The current in the circuit is equal to what? VTH by RTH plus RL or RX, anything you can say here. So this is equal to 10 divided by 8 plus 2, that is equal to 10 by 10, that is equal to 1 ampere current is flowing through the circuit, 1 ampere current. And this 1 ampere current, across this 1 ampere current, so what is the voltage drop across the terminal, between the terminal A and B? So here that is equal to I into 2 ohm resistance, that's why 1 into 2, that is equal to 2 volt voltage drop between the terminal A and B. So hence we can able to calculate the voltage drop between the terminals A and B. If you have a complex circuit, you can convert the complex circuit into the EG circuit, or the, you can see that there are only 3 components are there, the VTH, RTH and RL. Okay, so this way you can able to calculate the maximum power transfer theorem. Is actually, you can, this is the maximum power transfer theorem where the load resistance is variable, and you know the load resistance is equal to the source resistance, then only the maximum power can be transmitted from source side to load side, and we can able to find out the voltage drop across the load in a better way, and that is equal to what? V square over R, actually the power in the load, that is the maximum power, okay, in that case when the source resistance is equal to load resistance. Okay, we will discuss everything: Norton theorem, Thevenin's theorem, maximum power transfer theorem, superposition theorem, everything in the subsequent lecture. Now we'll discuss about the Norton's theorem, and we know the network consists of the resistors and independent sources, and here also the network is there. So assume that the network enclosed below is composed of the independent sources and resistors, and Norton's theorem states that the network can be replaced by a current source shunted by a resistance R. Okay, so now here the Norton's theorem, in the Norton circuit, the current source is the short circuit current of the network, and that is the current obtained by the shorting the output of the network, and this resistance is the resistance seen looking into the network with all sources deactivated, and this is same as the RTH. So here the actually RTH we can calculate as we already did in Thevenin's theorem, but ISS or Norton current, this is here the Norton current we can calculate with the help of by what? Sorting the output load terminal, and we have to calculate the what is the short circuit current across the output sorted terminal. So here we can able to apply the mesh analysis or whatever you know, the KVL, KCL, everything we can apply, we can able to calculate. But here what is the actually, you can able to understand the source transformation technique, that in the Thevenin's theorems we already calculated VTH and RTH. Here we are calculating the ISS and R Norton. So in view of the above, if we have the Thevenin's equivalent circuit in the network, we can obtain the Norton equivalent by using the source transformation technique. So this is actually the source transformation technique, and this is actually network from the Thevenin's theorem. Thevenin's, and this one is from Norton. So here Thevenin's and Norton's, this is the source transformation between them. So you can able to easily, if you have the Thevenin circuit, then you can able to convert it into Norton circuit, and if you have the Norton circuit, you can convert it into Thevenin circuit with the help of source transformation technique. So here, however, this is not Norton. We normally go about the finding the Norton equivalent circuit. Actually, we are actually doing the actual calculation of the Norton circuit. So now Norton theorem, based on Norton theorem, there is one question. So we have to find the Norton equivalent circuit to the left of the terminal A and B. Now the network shown below, connect the Norton equivalent circuit to the load and find the current in the 50 ohm resistor. So here the 50 ohm resistor is there. So 50 ohm resistor is actually the load here. So how we can solve this question by using Norton theorem. So here we can do it. We have to sort the output load terminal. we have to sort it. So and once you will sort, you have to calculate the ISS or IN, Norton current across the load. So in the next slide, you can see that the Norton current is actually the sorted current, short circuit current across the load. So here we can see that how we can calculate the short circuit current. So we can apply some KVL here. We can apply this one, Kirchhoff's current law or Kirchhoff's voltage law. So Kirchhoff's voltage law, here we can calculate. Let us assume this is the 50 ohm supply, the I1 current in the circuit, this is I2 current in the circuit. You have to find out the I2 current, okay, in this loop. So once you will calculate, you will get ISS is equal to 10.7 ampere. So here 10.7 ampere is the load current. Okay, so what we can do here, we can write down the 50 minus I1 times 20. Okay, so like this. Now after that you can solve. This is actually the I3, so you can write down I1 minus 20 minus, okay, plus I3 times 20, then minus 60 I1 plus 60 I2 is equal to 0. So this way you can able to write down the equation, and another equation you have to solve, and once you will solve, you will get the value of I1, I2, I3. And once this is the I2 current is actually in this circuit, that's why we can able to assume that ISS is equal to I2. And after calculation, this is actually 10.7 current ampere is the current on the load terminal. Now once you got the current on the load terminal, you can able to calculate the Thevenin's Norton resistance, as we already calculated in Thevenin's resistance. So same as Thevenin's resistance and Norton resistance is same, and that is equal to 55 ohm here. So now it can also be shown that by deactivating the sources, we find the resistance looking into the terminal A and B, and the RN and RTH will always be same value for the given circuit. The Norton equivalent circuit tied to the load is shown below. So here this is the Norton current or ISS, and this is the Norton resistance RN, and this is the load resistance RN. So here how you can, after this you can able to apply the what current division technique. So what is the current in the load? Current in the load is equal to IL is equal to, you can easily calculate 55 by 55 plus 50 into total current. So the formula is IL is equal to, you can write down RN by RN plus RN into I. So once you will calculate, you solve this one, IL is equal to 55 by 55 plus 50 into 10.7. IL is equal to 55 over 55 plus 50 is equal to 105 into 10.7 ampere. And once you will calculate this value, this answer is actually IL is equal to, you can write 11 here, and this is 21 times 10.7. Okay, this is your final answer. So in this way you can able to calculate the answer by using Norton's theorem or by using Thevenin's theorem.